Welcome to our first example on finding the resultant force using the analytical method for 2D forces. So in this example, I have this particle A right here, and I've drawn the x and the y axes right here in orange. And on particle A, we have three different forces acting on it. The first force is this 850 Newton force, and it is acting at 35 degrees above the horizontal. We have the 632 Newton force acting at 45 degrees below the x-axis. And then we have this 542 Newton force, and although there is no angle given at which this force acts, if we drew this force's line of action, we see that the intersection happens at this 6 meter and this 4 meter from the y and the x-axes respectively. So we can use these numbers to figure out what the angle is, or use it in other ways to determine the components of this particular force. So if you remember from the last video, there were three steps into figuring out what the resultant force of multiple forces are. The first step is to resolve each of the forces into their own components. So for each of these three forces, we are going to have to figure out the x and y components of this force. And then once that's known, step two is to find the x and y component of the resultant force. Now, the x and the y component of the resultant force, we tended to write as Rx and Ry. And the way that these were calculated was to take the summation of all the forces in the x direction, that would give us Rx, and we would do the same thing for Ry, where we had the summation of all the forces in the y direction, or the vertical direction. And once that is found, we can then go on to step three, which is finding the resultant's magnitude and direction. Now, the resultant's magnitude we can find using Pythagorean theorem, right? If we know Rx and Ry, then R is simply going to be the square root of Rx squared plus Ry squared. So anytime you're solving these sorts of problems, what I like to do is I like to set up a little table so that I can keep track of all the x components and all the y components of each of these forces, and then in the end we can just sum all those values for the Rx and the Ry components, and we can figure out what the resultant is. So over here, I'm going to start this little table, and I'm going to say that we have the first column is the force, whichever force that we're looking at, and then that force is x component, and then that force is y component. Now, all this is going to be newtons because the forces themselves are given in newtons, and we can use this table right here to keep track of the different components that we find. So let's go ahead and start with the first force, and you can pick whichever force you'd like. I'm just going to go ahead and do the 632 Newton force first, and so I'll do that here on the left. What I can do is for the 632 Newton force, I can say that the x component is going to be, well, if you look at this force, you know that it's going this way, and you know there's a little angle here of 45 degrees. So you can sort of see that the x component is going to go towards the right, and then the y component is going to come down, and that's how this resultant force, or the 632 Newton force, is going to be oriented. So you can see that this forms a triangle, so we can use sine and cosine to figure out what the sides are for this triangle, and that is our x and y components for that force. So for the x component, what I can say is that the cosine of 45 degrees is going to be equal to, well, cosine is adjacent over hypotenuse, and if I said that the x component is acting this way, I know that this is f of x for that force, and the y component is acting downward, so this is going to be f of y. So we're particularly interested in this f of x component because that's what we're finding first. So cosine of 45 degrees is going to be the f of x component, the x component of that 632 Newton force over the hypotenuse, which is 632 newtons. Now, if I rewrite this, I can rewrite it as 632 newtons times cosine of 45 degrees. And if I solve that out, I get a value of 446.8915 newtons. Okay, great. That is the f of x component. So in this table right here, I'm going to write the force that we're looking at right now is this 632 Newton force, and we just found out the x component of this force, and that is this 446.8915 newtons. Now, as you're solving these problems, make sure to keep track of the signs. So we know that the x component for this force is going to be to the right, so this component is going to be positive. The scalar value of the 632 Newton force in the x direction is going to be positive. Now, the y component, which is going downwards, we can use sine. So I can say the y component is going to be, well, that's sine of 45 degrees is equal to f of y over 632 newtons. And if I rewrite this out, it's going to be 632 newtons times the the sine value, the sine of 45 degrees. And this is also going to be 446.8915 newtons. And that makes sense, right? Because if this force is acting at a 45-degree angle, we know that the x component and the y component are going to be the same. So that matches up here, which is good. Now, I'm going to write this in the table here for this f of y value, but remember your signs. This force component is going downwards. So this force component, even though it's positive here, we know the direction of that force, and that's negative. So we need to take into account that negative sign. So I'm going to say it's negative 446.8915 newtons. Okay, great. So that takes care of the 632 Newton force. So I'm going to go ahead and erase all this, and then we can move on to the next force. The next force that I want to look at is this 850 Newton force. Now, this is going to be more or less the same. We're obviously going to get different components because the force is different. So let's go ahead and do that. Now, again, you'll see that this force is acting at an angle of 35 degrees above the x-axis, and so its x component is going to be this way, and its y component is going to be this way. So in this case, both components should be positive, and you can see that it forms a triangle here. So we can use this triangle to figure out what the sides of this triangle are. So for the x component, I can say that that is going to be 850 newtons times the cosine of 35 degrees. And cosine, because we're looking at the adjacent side, which in this case is the x component. And that turns out to be a value of 696.2792 newtons. Now I can do the same thing for the y side. I'm going to take 850 newtons, the hypotenuse, and this time I'm going to multiply by sine of 35 degrees because we're looking at this opposite side, right? The opposite side to this angle, that is sine. And if I solve this out, I get a value of 487.5399 newtons. Now, both of these values are going to be positive when we fill them out in the table here because, again, this force is going up and to the right, and so the x component is going to be positive and the y component is going to be positive. So back in our table for the 850 Newton force, we know that the f of x component here is going to be 696.2792 newtons. And the y component is also going to be 487.5399 newtons, and that's going to be positive, right? Okay, great. So now that we've figured out this force and this force, let's move on to this force. And this force is going to be a little bit more tricky, but it's not going to be too scary. So let's go ahead and do that together. Now, to start off, let's zoom into this force and see what's going on. I know that there is a force acting in the second quadrant and it is going up and to the left, and that has a value of 542 newtons. However, I don't have an angle, so I don't know what this angle is. I don't know what this angle is. I don't know what orientation this force is making. All I know is that it is in this second quadrant, and at some point along this line of action, we have a value of 6 meters here along the x-axis and 4 meters along the y-axis. Well, I can use this information to figure out what the orientation of this force is. So let's scroll back down and let's redraw this diagram so it makes a little bit more sense once we have some of that information. So down here, what I can do is I can say that, well, if I have a 6-meter long triangle here with one side is 6 meters and this side is going to be 4 meters, just like it was in the diagram, and the line of action for that force goes up and to the left, just like this, I can call this angle right here alpha. Now, if this angle is alpha and this is a right triangle, we can use Pythagorean theorem to figure out what the hypotenuse length is. And then once we know that, we can figure out the sine and the cosine values respectively. So let's go ahead and do that. Let's first say that the hypotenuse squared is equal to 4 meters squared plus 6 meters squared. And if I solve this out, I get a h value, the hypotenuse, is about 7.211 meters. So now that I know what this hypotenuse is, which is 7.2111 meters, I can now say, well, I can do the sine of alpha and the cosine of alpha. So the sine of alpha is going to be, well, sine is opposite over hypotenuse. So opposite is this 6 meters divided by the hypotenuse, which is 7.2111 meters. And then for cosine of alpha, that's going to be adjacent over hypotenuse, and that is 4 meters over the hypotenuse. And if we want to go one step further, we can solve these out in terms of their decimal values. You don't have to, but I will for the sake of this example. This is 0.5547. And for cosine of alpha, this turns out to be 0.8320. Now, we can use this information to figure out what the x component and the y component of that force is. So again, we're looking at this force right here, this 542 Newton force. So we know that the x component is going to go to the left, and in this case, it's going to be negative. And the y component is going to be going up. So the y component is going to be positive. So let's go ahead and do this one at a time. So let's go ahead and look at the x component first. Now for the x component, we can use our diagram, our triangle that we've drawn here to figure out what the x component is. So I know that the x component is acting horizontally. So I know it's going to be to the left and to the right. So that is this side of the triangle here. Now, normally when we've been figuring out what our x component is, usually we've been using cosine. But in this case, because the angle is here and the angle is opposite to this side, we know that we need to use the sine function to get the x component of this triangle, or the x component of that force. So I can say that the sine of alpha is going to be our f of x component over our 542 Newton force. So be careful. In most of the other forces, in both of these forces, the 850 and the 632 newtons, because we were using this angle and this angle, we could use cosine to figure out what the x component is, because the x component was adjacent to those angles. But in this case, we're using this angle, and the x side, or the x-axis, is going to be the opposite side to this angle. Now you could certainly also figure out what this angle is and then just use cosine to figure out what this x component is, and that'll work just fine. I just wanted to choose this one because, it's a little bit different. So back here, sine of alpha is f of x over 542 newtons. Well, we know what sine of alpha is. We figured out what sine of alpha was down here. It was this 0.5547. So if we plug that into our equation, or what I could do first is I could rewrite this as 542 newtons. I can just multiply 542 by both sides. 542 on the left-hand side, it's going to be 542 times sine of alpha, which was 0.5547. And that is equal to f of x. Now, f of x turns out to be 450.9713 newtons. So great, we figured out what the x component of that force was. It was 450.9 newtons. But remember, when we plug this into our chart, we have to take into account the direction. So again, this force is acting up and to the left, so we know the x component is negative because it's acting to the left here. So I can go ahead and write that into our chart for the 542 Newton force. This x component is a negative 450.9713 newtons. Okay, great. Now let's figure out what the y component of this force is. Okay, so for the y component, what we can do here is, again, we're looking at this angle right here, and the y component is vertical, and it's adjacent to that alpha angle. So in this case, we're going to say cosine of alpha, and I should probably do that in blue to stay consistent. I can say that the cosine of alpha is f of y over 542 newtons. And again, if I rewrite this, I get 542 newtons times cosine of alpha. Well, cosine of alpha was this value right here, so that is 0.8320, and that is equal to f of y. Now, f of y turns out to be about 300.6475 newtons. Now, remember, this y component is going to be positive because, again, this angle right here, or this diagram right here, we have this force going up and to the left. The y component is going up. So this value right here that we figured out, this 300, is going to be positive. So we can go ahead and plug that into our chart right here. And I can say that this is 300.6475 newtons. Okay, awesome. So that takes care of step one. We basically just did step one right here. We figured out what the x and y components of all these three forces were. Now, step two is a little bit easier. We can find the x and y components of the resultant force. And how do we do that? Well, we just sum all the forces in the x direction and all the forces in the y direction, and that gives us the x and y components of the resultant force, respectively. So let's go back to this chart right here, and let me draw a little line here. And what we can do is we can do our summation right here. And so if we sum all the forces in the x direction, we get a value of 692.199 newtons. And if we sum all the components in the y direction, the vertical direction, we get a value of 341.2960 newtons. Now again, this right here is our Rx component, the scalar value of our Rx component, and this right here is our Ry component. So great, we figured out what Rx and Ry were. Now, step three is find the resultant's magnitude and direction. The magnitude we can find using this equation right here, right? It's just a triangle. We can sum, or we can square both sides, add them together and take the square root, and we've figured out what r is. So let's go ahead and do that. We can say that r is equal to the square root of that rx squared component. So this would be 692.1994 newtons squared plus ry squared, and that was 341.2960 newtons squared. And we take the square root of that. And then if we do that, we get a value of r is equal to about 771.7661 newtons. Okay, great. So that takes care of the resultant's magnitude. Now we can figure out what the direction is. So how do we figure out what the direction is? Well, we need to look at the x and the y components of this resultant force. The x component has a positive value of 692. The y component also has a positive value of 341. So if I came down here and I said, okay, let me draw a x and y axis, a coordinate system right here. And this was our x-axis, and this was our y-axis. We know that the x component, this x component right here, this 692, is going to be to the right. And this is positive, so this y component is going to be up, or vertical. So I can draw out those two force components here on this axis that I've drawn. So this is Rx, and then Ry would be up here, and this is Ry. Now, to figure out the orientation of the resultant force, well, these two forces now are vectors because we've given them directions. So this is really Ry and Rx in vector form. Now, what can I do with vectors if I need to figure out their resultant? I can add them in a tail to tip fashion, right? So this Ry, I'm going to move over here. And now I can say that, well, now I know the direction of the resultant force, right? So if Rx is going some distance to the right and Ry is going some distance upwards, then I know that the resultant is going to be something like this, and it's going to make some angle here with the x-axis. Okay, so I'm going to go ahead and draw that r vector right here, this resultant vector, and I'll just call r. So we already know the magnitude of r. It's 771. The last thing we need to do is find the direction, which is this angle right here. So this looks like a job for our tangent function. So the tangent of theta is going to be opposite over adjacent, ry over rx in this case. And ry was 341.2960 newtons, and Rx was 692.1994 newtons. Now, if we just take the tan inverse on both sides, we get a theta value equal to about 26.2461 degrees. So great. Now we know the angle at which this resultant force acts. And so for our final answer, the resultant force for all three of these vectors acting on particle A, I'm going to write, let's just write it here by the diagram, so somewhere here. I'm going to write that the resultant force has a value of about 771.8 newtons, and the angle at which it's acting is in the first quadrant, and that theta value, or that angle, is 26.2 degrees. Great. There is our answer.